So you may remember the other day that I introduced you to the number 4. Of course, that was kind of fun. Got a few people to jump out of their seats a little bit and calculated 4 factorial as this product of all the integers starting at 4 down to 1. And in general, n factorial is going to be kind of likewise, n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. Factorial is a number that grows really big, really fast. Now, I introduced it the other day because it was part of a sequence, but we're going to use it today for something else. Our goal today is to expand binomials. And by that, expand a plus b to the n. What I mean is multiply it all out. So for instance, if I had a plus b cubed, when I say expand, I don't mean this. That's a kind of a cutesy answer that, might get you 1 point on an exam. But what I really mean is multiply it out. A plus b times a plus b times a plus b. And wow, make sure you don't give me the answer a cubed plus b cubed. Well, actually, if you did, you'd be making it very easy for me to grade. Instead, if you multiply it all out, multiply these together, and then you get a squared plus 2ab plus b squared, and then distribute the a plus b here. I'm sorry, that's a little bit of a mess. Eventually, you would end up with, a cubed plus 3a squared b plus 3ab squared plus b cubed. Wow, it's a lot of work. And that's only for something that have a cube. What if you have a 4th power or a 5th power? Then it becomes quite a challenge. So expanding this is going to require that we know how to do a little bit of work with what's called a combination. And so we're going to start out with that. And it's some notation that you should pick up on. It's n choose r. So n choose r, and there's a couple different ways you'll see it written. You'll see it written like this with the letter C. You'll see it written in a pair of parentheses like that. Either way, that's the formula. So let me write that down and choose R. And what this is, it's the number of ways you can choose a group of R objects from a group of N objects. And that number gets pretty big pretty fast. And we're going to calculate that. And let's do kind of a fun one here. Let's do it with the Michigan Lottery. So question is, how many ways are there to choose the 6 balls from a group of 47 balls in the Michigan Lottery? Now you should take out your TI-84 graphing calculator. Your 83 will do this as well. So here's the sequence of keys that you would type in to get that. You'll type in the number 47 first, and then we're going to go to this probability submenu from the math menu. So hit the math key. You can go to the left twice or to the right 3 times. Doesn't matter. You can scroll down a couple, or you can just type the number 3, then enter the number 6. So let's see what we do, or see what we get. I think we get about 10.7 million different possible winning lottery tickets. So where's my, oh, here it is. So 47, math key, or to the left to get the probability menu. And then I'm just going to type the number 3 to get to the number of combinations. I want to choose 6 of them. So 10.7 million. So nice. So that's example A. 47, choose 6. 10,737,573. So your chances of getting struck by lotto are less than your chance of getting struck by lightning, which is a little bit less than 1 in a million. Let's try a different one. Maybe you're a poker player and you want to know how many possible 5-card hands can be chosen from a deck of 52 cards. So that one would be 52, choose 5. And no, not that one. Let's see. This one here. So 52, choose 5. And it's going to be a little bit less than 2.6 million. So let's do that. 52, and then the math key, choose 5. So it's kind of a nice little calculation to be able to do and understand. There's more to this. If you want to take my statistics class, we'll cover part of it. It's kind of fun. 52, choose 5. Yeah, just under 2.6 million. 2,598,960. Yay. So not bad. Now, if WebAssign is giving you a problem like this, it might look a little different. They might just use this notation. So that's example B. And what I'd like you to do is calculate 5, choose 3, and tell me what you get. Put it in the chat, please. So you should end up with 10 from this. So kind of a small number. This is a number that we're going to use later on in calculating the coefficients that you're going to need to expand those kind of things. So, all right, let's keep going. Now, the way we're going to work on expanding these things is with something called Pascal's triangle. And I'll talk about Pascal in a little bit. Blaise Pascal was a French mathematician who lived in the 1600s. Although he didn't actually discover the triangle that bears his name. Nonetheless, let's look at Pascal's triangle. The way Pascal's triangle works is it's going to start out with a 1 at the top. And then each layer down, you're going to put 1 on the outside. So 1 on the outside, 1 on the outside. And each layer is going to get bigger and deeper. But the numbers inside are going to come from adding up the 2 numbers above. So 1 and 1 gives me a 2. Okay, not so bad. Let's look down at the next layer. 1 and 1 on the outside. What numbers are going to go in the middle? 3 and 3. Well, let's do one more together, and then I'll let you do one. So 1 and 1 on the outside, and then 4, 6, and 4. All right, so you try one. Try putting 1s on the outside and adding up to get numbers in the middle. Pascal's triangle has an incredible amount of interesting things embedded in it. You know, for instance, these numbers are the counting numbers. These numbers are going to be triangular numbers. These are going to be your tetrahedral numbers, and I'll talk about that in a little bit. But for now, you should get 5, 10, 10, and 5. All right, so this is nice. It's cute. It's pretty easy to come up with. But a good question to be, well, what's the significance of all this stuff? And the significance is that these are the coefficients you get when you expand a plus b to the n. So let's take a look at that. Here we go. If you take a look at Pascal's triangle here on the left and compare it to your binomial expansion on the right, you should see a nice correspondence in the coefficients here. So the coefficients here for a plus b to the first power are 1 and 1. Oh, we got 1 and 1 there. 1, 2 and 1, 1, 2 and 1, 1, 3, 3, 1, etc. So there's a nice correspondence between these coefficients. And this is going to lead to a nice shortcut in expanding these binomials. So for instance, instead of multiplying a plus b by itself 4 times to get this, you're going to start out with a to the 4th power, b to the 0 power, which isn't written here, but it could be. And then as you move from left to right, you're going to slowly decrease the powers of a and increase the powers of b. So a to the 3rd, a to the 2nd, a to the 1st, and then a to the 0. Well, that's 1, so I don't need to write that. Meanwhile, the powers of b increase from 0 to 1 to 2 to 3 to 4, etc. So there it is. There's your a plus b to the 4th power. You throw in the coefficients, and you're done. A lot faster than what you would get if you had to multiply it out by hand. So let's see if we can't replicate something like that with x plus y to the 5th power. Just kind of a nice little intro example to this. So let's see here. Let's do x plus y to the 5th power. And let's see. Let me start out by writing the terms here. Now, I'm going to use this line here from Pascal's triangle. That 5 here and that 5 here matched. So it's the 6th line down. 1, 2, 3, 4, 5, 6. But it's this one here. Now, we'll do it this way. Let's start out by writing all the powers of x and y. So it's going to be x to the 5th, y to the 0, plus. Now leave a little space here. I'm going to need to fill that in. And then the powers on x decrease and the powers on y increase. X to the 4th, y to the 1st, plus. Again, leave a little space here. X to the 3rd, y to the 2nd, x to the 2nd, y to the 3rd, and so on. X to the 1st, y to the 4th. You don't necessarily have to write to the 1st power. I did that initially just to try and get you in the pattern of things. And finally, x to the 0 power, y to the 5th. Again, you could omit x to the 0 power because x to the 0 power or anything to the 0 power is 1. Now, let's drop in the coefficients. That would be these: 1, 5, 10, 10, 5, and 1. So are we looking okay so far with this one? This is kind of a nice intro example. We should clean it up a little bit. For instance, I don't need to write x to the or y to the 0, so I'll just write x to the 5th plus 5 x to the 4th y plus 10 x cubed y squared plus 10 x squared y cubed plus 5 x y to the 4th plus y to the 5th. And that's it. You're done. So we've got x plus y to the 5th power. A lot easier than multiplying this by itself 5 times and collecting like terms. Yeah, I would never do that. Comments or thoughts on that first one? We okay there? All right, let's try some more here. So let me come back up to the top. That was example D. Write that down. Example D. Let's try example E. So kind of bumping up things in terms of level of difficulty. And so copy this one down. It's going to be 5x minus 2y to the 3rd. You know, I think maybe we should do kind of an intermediate example. No, this one won't work. We'll make this one work. All right, this one's going to be a little bit harder for a couple of reasons. First of all, we've got a plus, or we got a minus there instead of a plus. So that's going to be one change that we're going to have to deal with. Secondly, our terms aren't just an x and a y or an a and a b, so we're going to have to figure that out. The first thing I would do is to suggest we need to rewrite this, because I need 5x plus something. How can I rewrite this so I have a plus something there? What would I put in there?
Minus a negative.
Yeah, plus negative 2y. And so from the viewpoint of Pascal's triangle and expanding things, that's going to be your A and that's going to be your B. Awesome, thank you. So this term we're going to start out by writing it as 5x cubed times negative 2y to the 0 plus, and then leave a little space here, 5x squared times negative 2y to the first power plus, and again, leave a little space there to write in some coefficients. 5x to the first power, I'm just going to leave it as not written, negative 2y to the second power. And last but not least, 5x to the 0 power, negative 2y to the third power. Okay. Well, so far so good here, but we got to make sure we remember one important thing, and that is I need to put in the coefficients from Pascal's triangle. So let me replicate that here real quick. 1, 2, 1, 1, 3, 3, 1. So the fourth row is going to go along with this. By the way, if you have something to the third power, you're going to have 4 terms. If you have something to the fourth power, you're going to have 5 terms. So this number helps you decide how many terms you're going to have. My coefficients here across are going to be 1, 3, 3, and 1. So this will get you partial credit if you get this far. But of course, I'm going to want a little bit more here. Are we okay with how we set this up? It's just your A and B within the appropriate powers, and then throw in the coefficients from the third line of Pascal or fourth line of Pascal's triangle. All right. We need to cube these out and take care of them. What's something to the 0 power?
1.
Yeah, something to the 0 power is 1. Thank you. Now, this is going to be 5 cubed times x cubed. 5 cubed is 125. And then I'll have an x cubed. And that's it. All right, let's keep going. Plus 3 times, well, 5 squared is 25, x squared times negative 2y. And then 3 times 5x. What happens when I square negative 2y? What am I going to get there? Well, negative 2 squared is 4. And then y to the second power is just, yep, 4y squared. And the last term, anything to the 0 power is 1. So I'll end up with negative 2 cubed, which is negative 8, and then y cubed. So I'm not trying to do it all at once. I'm trying to do it slowly so you can see the pattern here and how this is working. The last thing I'm going to do is kind of multiply and clean this up. So that's going to be 125 x cubed minus 2 times 3 is negative 6 times 25 would be negative 150 x squared. 3 times 4 times 5 is going to be 60. X, you know what? I forgot a y here. There's a y in there. And then x, y squared, and finally minus 8y cubed. There we go. I think a lot more user-friendly than having to multiply it out and collect like terms. But you tell me. If I went over something a little too fast here and you need me to fill in some details here or there, let me know. I'd be glad to go over that, help you out. Doing good on that one? All right. Let's try another one. So I'll call this one example F. And let's do 4a minus 3b to the 4th power. So this time we're going to need the 5th row from Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So when you expand this, you're going to have a total of 5 terms. And these are going to be the coefficients of your 5 terms. I would start by writing that as negative 3b or plus negative 3b, like that. And let's go across much in the same fashion we did here. Raise that to the 3rd power and this to the 0 power, and then start decreasing and increasing from left to right. So maybe if you're watching this later, you want to pause the video and try and write this down for yourself. That's a great idea. For us, let me just kind of proceed here. It's going to be a 4a to the 4th times negative 3b to the 0 plus. And leave a little space here. 4a to the 3rd, negative 3b to the 1st. Again, leave a little space. 4a squared, negative 3b squared, plus little space. 4a to the 1st power, negative 3b to the 3rd power. And finally, over here at the edge, 4a to the 0 power, negative 3b to the 4th power. One little thing that I'll point out about the exponents at this point, they always line up. They always add up to this exponent here, 4 and 0, 3 and 1, 2 and 2, 1 and 3, 0 and 4. They should always add up to that exponent there. Now that'll change if you start getting things like an a squared term or a b to the 3rd term, whatever. But at least initially they should line up like that. Now let's take the coefficients from Pascal's triangle. 1, 4, 6, 4, and 1. By the way, Pascal's triangle should always be symmetric. It should never be anything other than symmetric. So as you go across from left to right, that you should have a repeating pattern. Now you can take out your calculator to help you out with some of these. 4 to the 4th power is 256 times a to the 4th times 1. So just 256 plus. And let's do it kind of slowly here. 4 cubed is 64, a to the 3rd power times negative 3b plus 6. And here I've got to work with both terms. So the first one is going to give me 16a squared times 9b squared. And hopefully doing it slower like this will help you out. See where these things are coming from. 4a, negative 3 cubed is negative 27, b to the 3rd. And last but not least, and I'm not going to try and cram it in there, I'll just put it over here, plus 1. Something to the 0 power is 1. So times 1 times 3 to the 4th power is 81, b to the 4th. So not a bad idea to do this in a couple steps rather than try and do it all at once. You can, I'm not going to stop you. 256, a to the 4th. 4 times 64 is 256 times negative 3, negative 752. No, negative 768.
768.
Yeah, 68. Negative 768. A cubed b. Let's see. 16 times 9 is 144 times 6. I don't feel up to doing that one in my head. Let's see. That's 644. Let's see. 852. 8 what?
I got 864.
Yeah, 864. Thank you. A squared, b squared, plus 8 times 27. Is that 216? 27 times 8. Yeah, 216. except it's going to be a minus 216. So let's see. I don't have any Photoshop here. So I'll just write it like this, minus 216. A to the first power, B to the third.
Shouldn't it
And
be 432?
That's what I got too.
So you have 432?
I think you added the 4s to get an 8
Oh,
instead
yeah,
of
I did. I
multiplying
did.
them.
Yeah, I did. Thank you. So minus 432. And finally, plus our 81b to the fourth. Thank you on that. I appreciate you double checking me. Awesome. That's your final answer. Now, it's not the easiest, but it's a lot more user-friendly than having to go through and multiply and add up all the like terms. If I was more ambitious, I would show you all the work that would be involved in something like that. It's a pain. How are we looking on example F here? Okay. Let's continue to make these a little bit more challenging. So example G. Let's try, let's see, we'll do 5a squared minus 3b to the fourth power raised to, I don't know, feel ambitious, you want to go for the fourth power or the fifth power? How ambitious are you today? We'll stick with the fourth power. These numbers are going to get pretty big as they are. So that term is your first term, and this one's going to be your second term. You might want to rewrite that as 5a squared plus negative 3b to the fourth, like that. So that's our A and that's our B. You want to write them like that. I'm going to write it in a smaller pen because I'm going to run out of room here, I think. So let's do it this way. And let's see, it's going to be 5a squared to the fourth power and negative 3b to the fourth to the 0 power. Does that show up okay? Can you see that clear enough? Let me make that a little bit bigger. All right, let's keep going. Plus, leave some space. 5a squared cubed times negative 3b to the fourth power raised to the first power plus 5a squared squared times negative 3b to the fourth power squared plus 5a squared to the first power, which I'm not going to write, and negative 3b to the fourth power raised to the third. The last one's going to be 5a squared to the 0 power. I'm going to skip that because I'm running out of room and just write negative 3b to the fourth power raised to the fourth power. Now I need to throw in some coefficients. Those coefficients come from Pascal's triangle. Those coefficients are going to be the same as they were for the last one, which was 1, 4, 6, 4, and 1. So let's drop those in and then start cleaning things up. So 1, 4, 6, 4, and 1. At this point, these exponents all add up to 4. 4 and 0, 3 and 1, 2 and 2. It's not going to be the case after this one, though. So what's going to happen? Well, let's start with 5 to the fourth power. That's going to be 625. And what about a to the second raised to the fourth? Do those exponents add or multiply?
Add,
Oh,
multiply.
yeah, multiply. Thank you. A to the eighth times 1, which I can ignore that part. Let's keep going. It's going to be plus 4 times 5 to the third power is 125. A squared to the third power gives you a to the 6th times negative 3b to the 4th. Let's clean up this one right here. Now there's two things you got to do. You got to square this term and square this term, and then we'll multiply it all out. Let's start by squaring each of those terms. Six, 25. This is kind of an odd case. If you were adding, you get the same thing as what you multiply, 2 plus 2 or 2 times 2, but it's a multiplication. So 25a to the 4th. And then what happens when I square negative 3? Negative 3
It
times negative
becomes
3,
9.
positive 9, b to the 8th. And plus 4, 5a squared. And that's going to be negative 3 cubed, which is negative 27, b to the 12th. And the last one, negative 3 to the 4th power is going to be 81. B to what power?
16.
Yeah, b to the 16. Thank you. Let's go through and see if we can't clean that up a little bit. $625, a to the 8th. 125 times 4 is going to be 500 times negative 3 is going to be negative 1500. A to the 6th, b to the 4th. How about here? 6 times 25 is 150. 150 times 9 is 1350. So plus 1350. A to the 4th, b to the 8th. 2 more terms. 20, 4 times 5 is 20 times negative 27 is negative 540. So I need to make that a minus here. 540. A to the 2nd, b to the 12th. And finally, plus 81, b to the 16th. Nice. And that's it. That's your final answer on that one. These binomial coefficients oftentimes correspond towards probabilities. But it's also nice if you're working with something that you can expand this without having to multiply it out term by term by term by term. That's a real drag. All right, let me just kind of do a spot double check here. And also check in the chat. Okay, so example H. This one's going to be a little bit of a challenge. 1 over x minus the square root of x. I hate going back to the 4th power, but we're going to do this one with the 4th power again. I think these ideas generalize pretty easily to 5th power, 6th power, whatever you need. Before we get going on this, I would strongly suggest you rewrite this. Now, the first step, of course, would be to write it as maybe plus negative square root of x, like that, to the 4th power. But I want to rewrite it again one more time. Any suggestions as to how I'd rewrite that? Is there another way to write it so I have, say, x to some power?
is it 1/2?
All right, so x to the 1/2 here.
X to
Good.
the power of -1.
Yep. X to the -1 power here and negative x to the 1/2 here. So that's going to make it a little bit more challenging to deal with because you've got these different powers of x's and we're going to have to eventually combine them. We're going to use the fourth row of Pascal's triangle. So keep that in mind, keep that handy. Let's start out with writing all these terms. It's going to be x to the negative first power raised to the fourth. And then, I don't know, I think this might be the last time I write this. Negative x to the 1/2 to the 0 power. And then x to the negative first power cubed, negative x to the 1/2 to the first power. I'm just going to leave it as is, plus x to the negative first power squared, negative x to the 1/2 power squared itself. And let's see what else. Plus x to the negative first power and negative x to the 1/2 power cubed. And finally, negative x to the 1/2 power to the fourth power. Technically, you got x to the negative first power to the 0 power, but kind of run around and run, so I skipped that part. Somebody tell me what coefficients I want to put in here. Could also have these just about memorized by now.
1, 4, 6, 4, 1.
Yep, perfect. Just the fourth row of Pascal's triangle, 1, 4, 6, 4, 1. Make sure that the numbers you put in are always symmetric when you start. So 1, 4, 6, 4, and 1. Now comes the tricky part. Cleaning up this mess. So 4 times -1 is x to the -4 times this, the 0 power, which is just 1. So I'll just leave that there. And then I'll have a 4 times -1. So I'll have a -4. What's going to happen with these exponents? We've already dealt with that in example G, but what happens to these exponents?
They get multiplied.
They get multiplied. So I had number 4x to the -3rd. I already took care of the negative. So I'll have times x to the 1/2. And let's keep going. Plus 6 x to the -2nd. And then when I square this, negative times a negative is going to disappear. But how about the exponent? What exponent am I going to get?
One.
Yeah, 2 times 1/2 is 1. So I'll get to the first power. I'll actually write that here.
Wait, wouldn't it? Oh wait, is it -6 because of the negative x?
It's a great question. When you square that, it becomes positive. So it would be a +6 there. It's a good question. But if you take a look at negative x to the 1/2 squared, that's negative x to the 1/2 times negative x to the 1/2 again. Negative times a negative is positive. X to the 1/2 plus 1/2 gives me x to the first power, or just x. So yeah, it's a good question. Like I said, it gets a little tricky down here with simplifying all these fractional powers and stuff like that. But did you follow me? Are you comfortable that that's just x to the first power there?
Can I see what you just wrote down one more time, please?
Yeah, sure. Right here. When you square something, that's like multiplying it by itself. So negative times x to the 1/2, negative x to the 1/2. Negative times a negative is positive, and then add up the exponents. 1/2
I
and 1/2.
think someone might have asked that because it kind of looks like the plus in front of the 6 kind of looks like a plus that you scribbled out and tried to make a subtraction sign. That might be why someone asked that. I don't know.
Okay, I appreciate that. that's a plus there, and it's still a plus here. Okay. Over here, let's see if we can't figure out if this is going to be positive or negative. It's going to be 4 times this to the third power. Now, if I have something negative that I raise to an odd power, am I going to get a negative or a positive out of that?
Negative.
Yeah, I should get a negative. In fact, let me do that real quick here. If you're calculating negative x to the 1/2 cubed, you could think of that as negative x to the 1/2 times negative x to the 1/2 times negative x to the 1/2. A negative times a negative is positive times a negative gives me a negative. And then add up the exponents. 1/2 plus 1/2 plus 1/2. Well, that's really 3 times 1/2, or negative x to the 3/2. So that's what comes out of this, is plus 4x to negative first power, and then negative x to the 3/2. How about that last term? What am I going to end up with from here? First of all, am I going to get something positive or negative? Yeah, you're going to get something positive because you got a negative to an even power. So you're going to get something positive. And 4 times 1/2 gives me a square. 2. Okay. So that one's pretty challenging to pull that one all together. Now, we still have some simplification we can do. Let's circle this. That's this line. Let's simplify this. Now, is there a fancier way or another way I could write x to the negative 4th?
1 over x to the 4th.
Yeah, 1 over x to the 4th. And then this, well, let's see, if you add exponents, that's negative 3 plus 1/2. That's negative 2.5. So, I'm going to do this in 2 steps. Do 4x to the negative 2.5 is also 5/2. Add exponents here. I'll get 6x to the negative first minus times a plus is going to be a minus 4x negative 1 plus 3/2. Well, that's negative 2/2 plus 3/2 gives me 1/2 plus x squared. Last but not least, I like to get rid of the negative exponents. Not that you have to, unless I say so on the exam. That'd be x to the 5/2 in the denominator plus 6 over x to the first power minus 4 x to the 1/2 plus x squared. And that would be your final answer there. Okay. Don't worry. At most, I put like 8 or 12 of these on the exam, so it shouldn't be bad. All right, just kidding. You probably get a couple like this, one easier, one harder. Give you a chance to show me what you know. But do expect kind of a basic one, much more basic than this. Something like our first few examples. You will get one like this in the homework. So if you're not sure about this, reach out, let me know. Get some help. Okay. Well, let's kind of pause for a moment. And let me check out the chat first. All right. Thank you. Appreciate the feedback. I mentioned earlier that some really cool things you can do with Pascal's triangle. Some really cool properties. So let's go over some of those just to show you how the tip of the iceberg of just how amazing Pascal's triangle really is. So first things first, it was named after Blaise Pascal, who was a French mathematician who lived in the 1600s. Some interesting things about him. There's something called Pascal's wager that you probably study if you study religion. He was, at times in his life, he was very religious. He died pretty young. He was like 39 years old. So, but here's his triangle. We've gone over that. But here's some kind of fun things. So I mentioned earlier that the numbers along this side, other than your counting numbers here, these numbers are your triangular numbers. What are triangular numbers? Good question. Well, to recognize these, if you've got bowling or just played around with things in other ways, these are your triangular numbers. So down that side, you get triangular numbers. What about the next column here? I mentioned those were your tetrahedral numbers. Well, if you start stacking these, a 1 plus 3, and then 1 plus 3 plus 6, then you get the tetrahedral numbers. So tetrahedral numbers, that's going to be how many of these balls there are at any particular level of your stack. So the first two levels, there's a total of 4 balls. And then you add 6, you get 10, and then 20, etc. So those are your tetrahedral numbers. Pretty cool. When we introduced sequences, we talked about Fibonacci and his sequence. And yeah, Fibonacci numbers, they're in Pascal's triangle as well. And here's a different look at it, maybe a little less busy, so you can kind of see that. Nudge it up a little bit. There you go. There's your Fibonacci sequence. Wow, Fibonacci is everywhere. Yes, it really is. Powers of 11. 11 squared is 121. 11 to the third power is 1,331. 11 to the fourth power, and so on. Now, after the fourth power, it gets a little murky, but there is a way to kind of recover that pattern. And just one last couple things about Pascal's triangle. This is something called Sierpinski's triangle, and it's an iterative process. At each stage, you take out kind of like the middle third of these triangles, you lighten it, etc. Now, if you keep on doing this for a long time, you get a shape of something called a fractal. And what's going to happen is that if you zoomed in at any level with a magnifying glass, you'd see the same original pattern. So it's kind of cool. It's amazing. It's called a self-similar shape. Well, let's bring that back to Pascal's triangle. If you color the odd numbers black and the even numbers white, then you're going to get a Sierpinski triangle. It's really cool. And of course, this Valentine's Day, you can remember your sweetheart with Sierpinski's Valentine. Yay, cute. One last one. If you pick any number in Pascal's triangle and then look at the alternate numbers around it, 10 times 6 times 35 will equal 5 times 20 times 21. Both of them equal 2,100. There are a ton more patterns here, but I digress. Oh, there you go. Across here, you'll find powers of 2 if you add those up. I mentioned Pascal didn't originate his triangle. Here's Pascal's triangle in Chinese back in 1303. And even then, it was referenced as the old method. So, wow. Japanese, Hebrew, etc. It's gotten around. But let's finish this up. We got to finish up with something called the binomial theorem. You may remember at the start of this that I had you calculate these things and choose R. Now, the usefulness of that is if you have to calculate something pretty far down the list of Pascal's triangle. Say, for instance, something like 2x plus 7 to the 18th power. If you're stuck getting the coefficients for the 18th or 19th row or the 22nd row of Pascal's triangle, that might put a little damper on your day. So it'd be nice to have a little formula then that you can fall back on. And this is the formula. It's called the binomial theorem. So let's see if we can't put it into practice. You're going to have to figure out what your A and what your B and what N is, and then fill in this formula. So I'm going to copy down that formula onto my sheet so we can fill it in. So A plus B to the nth power going to be sum from, now they chose the letter R equals 0 to N of N, choose R, and then A to the N minus R and B to the R power. Great. Let's see if we can't do our first example up here, which I think I passed it a little bit. Suppose you want just the first 3 terms in this expansion. So I've got x plus 5y to the 22nd. That's what I'm looking for. So this is my A, this is my B. I kind of know what's going to happen with the first 4 terms, or first 3 terms. I'm going to start out with A, B, start with x to the 22nd, and then 5y to the 0 plus x to the 21st times 5y to 5y to the first power. And then let's leave a little bit more space, x to the 20th and 5y squared. Now that's all well and good so far, but what I don't have are the coefficients. And that's where this comes in. So if I do r equals 0, r equal 1, r equal 2, up here in the summation, at r equals 0, well, let's see. That's my n. It's going to be 22, choose 0. And then the next term is going to be r equal 1, 22, choose 1. And then 22, choose 2. Those are going to be your coefficients as you start Pascal's triangle. Can anyone guess what 22, choose 0 is going to be? And I don't want you to guess based on the calculation. I want you to base your guess on what you know about Pascal's triangle.
It would be 1.
Yeah, be 1, right? Now, a way you can kind of interpret that in terms of choosing things, there's only one way you can choose 0 objects out of 22. So it's just a 1. Remember, Pascal's triangle always starts out with a 1. So 1 times x to the 22nd, that's just 1, so it's just x to the 22nd. How about this one? Can we do this one by thinking? If you're going to choose one object from a group of 22, how many choices do you have?
22.
22. Nice. And it'd be x to the 21st times 5y, and then that's going to be 110. This one, you might want to bust out the calculator. 22, choose 2. 11 times 21. 231, 221, 231. I don't know.
Yep.
I'm not a
231 exactly.
231. All right, awesome.
Yeah.
231 x to the 20th times 25 y squared. Okay, so not so bad. X to the 22nd plus 110, x to the 21st plus, I'm definitely going to bust out the calculator on that one, times by 25, 5,000, oops. Can anyone tell what I forgot here? what did I forget from this product right here?
Why?
The y, yeah, forgot the y. Let's squeeze in the y there. And last but not least, it's going to be 5,775 x to the 20th y squared. Now, this is some other stuff, but all they asked you for was the first 3 terms. So, yay. How's that one looking? Is there anything on that one that's still a little bit concerning? Maybe you want to follow up with something. Maybe there's someplace I can add some more detail. All right. There's nothing wrong with the binomial theorem. Nothing. Certainly, it would ruin your day if you had to work all the way down to the 22nd level of Pascal's triangle. That would be a major bummer. I do have a different way you can come up with these coefficients. And it's nice because it doesn't necessarily revolve on that formula. It's quick. So let me just highlight the coefficients I'm talking about. This one, and this one. How do you come up with those? Well, the first one's always going to be 1. But to get the next coefficient is going to equal the previous coefficient, times the exponent of a divided by the number of the term. It looks like a mouthful. It kind of is, but in practice, it's not all that bad. Let me rewrite this down here. 1 x to the 22nd plus 22 x to the 21st, 5y, etc. And then I had x to the 20th times 25y squared. But I need to fill in these coefficients. So let's see. Well, this says if I want the next coefficient, I'm going to take the previous coefficient times this exponent. So 22 times 1 is 1, divided by the number of the term. Well, this is your first term, this is your second term, this is your third term. So if I want the next coefficient, it's going to be 1 times 22 divided by 1. That tells me my next coefficient. And let me move that up a little bit. How about if I do it again? Well, if I want this coefficient, for instance, I'm going to do the same thing. It's going to be the previous coefficient times that exponent divided by the number of the term. So in this case, it would look like 21 times 22 divided by the second term. And that would give you 231. Nice. Let's see if we can't figure out the next coefficient. It's going to get pretty big, isn't it? But, you know, it's that or use the binomial formula. Doesn't matter to me. Whichever one of these works for you is fine. So you can go back to the binomial theorem. It'd be 22, choose 3. Or if you got this pattern down, what would I multiply by? What would I multiply what times what divided by what?
231 times 20 divided by 3.
Perfect. This times this divided by the third term. So I think that's going to be 77 times 20 should be 1540 maybe. Let me just double check that. So 231 times 20 divided by 3. Yeah, 1540. So that'd be your next coefficient. And you can keep on doing that as long as you need to. So whatever works out is fine. That'd be x to the 19th. And then 5y to the third would be 125, y cubed, etc. But you're only going to use the exponent from your first term, all right, before you start doing any work to simplify that. It's up to you. We'll practice one more. You can do these either way you want. You can do it with a binomial formula up here, or I can use this little gimmick down here. Whatever is easiest for you. So let's see. All right. We'll do H or I. Which, any preference? H or I? Okay, I. We'll do I. So our last example. Example I. 3x minus 4y raised to the 22nd power. We want the first 3 terms of that expansion. So this down here. All right. If you're watching this later, pause the video. If you're watching it now, you can work on it. Okay, so we'll rewrite this as 3x plus negative 4y all to the 22nd. And let's write out the first few terms, at least in terms of the pattern. It's going to be 3x to the 22nd, negative 4y to the 0. I'm not going to bother putting it here this time. And then the next one is going to be 3x to the 21st and negative 4y to the 1st. And I'm going to leave a lot of room here. 3x to the 20th, negative 4y to the 2nd. So we got to fill in some numbers here. Now you can do that a couple different ways. You can do it with binomial coefficients. Now I guess I would start out with this. You always know that's 1, right? And then the other one that you always know is that this is going to be 22 here. So you can get those essentially for free. So it's a matter of what do you want to do to calculate this third one here? You could do a couple things. You could do 22 choose 2. That would tell you it. Or if you're partial to that little trick that I did last time, you could do 21 times 22 divided by what? Divided by the number of the term. Remember, this is your first term. This is your second term. So you divided by 2. And I think we're back to one that we've done before. You know what? I screw up. Yeah, we kind of did one just like this just a minute ago. But that's going to be 231 here. Now, to finish this off the rest of the way, you might need to calculate 3 to the 22nd power on your calculator. I'm not sure what WebAssign is going to be asking you. So that's going to be pretty big. Let's see here. Let's clear that and clear this. So 3 to the 22nd, 22. Wow. Yeah, I'm thinking that they probably don't want you to write all that. So at least for me and for the exam, you can just leave it as 3 to the 22nd. Because those are just enormously big. So 3 to the 22nd, x to the 22nd, and then 22 plus or times 3 to the 21st times -4. And then x to the 21st, y. We could probably take care of this and write it as -88 times 3 to the 21st, x to the 21st, y. And last but not least, 231 times 16. Let's figure out what that is. 16 being 4 squared or -4 squared. So it'd be plus 3,696 x to the 20th, y to the 2nd. And I need to times 3 to the 20th in here. I should probably put that out in front. My bad. Okay. That's about it for section 12.6. Any last minute thoughts or questions here before I wrap it up? All right. You still have a test on Monday. Yeah, go ahead. Question.
Where did the -88 come from?
-4 times 22.
Gotcha.
I just put those two together.
Okay.
A little bit cleaner. Yeah, but these numbers and their powers, they're just too big to really mess with. So
Just leaving them.
yeah, I'm just leaving them there.
Okay.
Yeah. All right. Any other thoughts or questions? Okay. Well, like I said, you do still have a test on this, so hopefully keep up with it. If you have any questions, please reach out and get some help.